NAGI, so his audio is off, and I hope he's with us or not. Anyway, so I'm going to record the class, and I'll send it to everybody anyway. But so I want to preface it by saying that this is not a substitution to actually getting the manual and reading it, right? So this is a cram course to hopefully see if you can pass the exam based on your knowledge base on the technician, and then a little bit here on the general class. So I'm going to be referring to the notes I sent out kind of extensively. Okay.
So question, Joe, are you going to still be having a course starting on the 31st?
I don't know I believe so. I don't know the answer because my wife is the one who schedules the classes, and she's not here at the moment. Okay. So I'll have to send everybody an email. I don't know the answer.
Understand. Okay.
I don't know at the moment. Yeah. So it depends how many people signed up. If I don't have at least 5 people in the class, then I don't run the class, and that's the criteria. Right. So I don't know how many people signed up to the general class. Okay.
Okay.
So with that said, I encourage you to either read the manual, or actually I have some videos. Hold on. That's my cohort in crime here. Hold on. Okay, so what we're going to do, Wayne, I'm going to do this for 1 second. Lou, who's my partner here, is kind of watching what I'm doing because he's going to. He wanted to see how I run the classes. So what we're going to do is I'm going to call in again in just a second. Okay? On a speakerphone.
Sure, no problem.
All right, so hang in there.
Okay.
Hey, can you guys hear me okay?
Yep, gotcha.
All right, good. So I got you on speakerphone because Lou's right behind me, and he's kind of looking over my shoulder. So hold on 1 second. So Lou, that's my display, and I can see what the audience sees, and my attendees are here. And I have Dave Akins in here. I don't know why, but he's here. So I have Patrick, Wasim, Wayne, and that's it. Okay, anyway, so what I did, Lou, was I kind of explained to them that this is a cram course and that it in no way should be substituted for a real general course or for listening to the manual. Okay, so, and as to whether I'm running the general class or not, I don't know. My wife is the one who makes up the schedule, so I'd have to get back to you, Wayne. Okay? Patrick, I see you're on. Wasim, I think you're on. So if you have questions, just unmute your phone and give me a holler. So I'm referring to the sheet that I gave you, the study sheet, and we'll go through it kind of a little bit quickly, and then we'll refer to the manual as well. Okay? So, and the manual that I'm using is the ARRL General Manual, so it's by the same people. So the whole idea behind general class is to give you more privileges on HF, and with that privileges invariably comes more power. Okay, so even I, being a QRP guy, I started with 100-watt radios, and I played with amplifiers for about 3 days. Didn't like that at all, and then I decided to become a QRP person. But the reason that they separate the licenses is because when you go to HF, there's a little bit more to it. So in general, we're really learning the same stuff. We're just going into it a little bit deeper so that you don't accidentally nuke your dog or hurt yourself or whatever. So the stuff that's on these 2 pages that I gave you is the basic minimum amount of information that will probably get you to the exam. Okay? So when I tell you that you need to know everything that's on here, well, I really mean that. Okay? So these are all part of the question pools of the 5 different general exams that they give. This is the questions that are on one of those 5 exams, or maybe more of them. Here on the frequencies chart, okay, the ones you need to know are in bold. So 10 meters, you need to know that. 12 meters, you need to know that. Okay. 15 meters, this is what you need to know. Okay, just this part here. All right. 20 meters, you need to know this part. All right. 30 meters. And Wayne, you know that 30 meters, we can't use what on 30 meters?
30 meters, you cannot use any telephone on that or voice or anything like that.
Yeah, it's not telephone, it's phone. That's correct. Excellent.
Right.
Excellent. 40 meters is here. Okay. 60 meters. 60 meters is kind of a unique band, and we're only allowed to use 5 authorized channels. And the reason is we share 60 meters with 2 different governmental agencies. So we can only use 5 separate channels. 80 meters, 120. So I listed here that bolded items are in the question pool. All right. You're okay with that, right? Patrick, your audio isn't on, but if you have any questions, you can type them in, and hopefully I'll see them, okay? They talk about power. And power, we can measure power in a whole bunch of different ways. One way to measure power is PEP, which stands for peak envelope power. And what that means in English is the amount of power leaving your antenna cannot exceed this value. Okay? Peak envelope power. So no matter what you do, downhill with the wind, you know, whatever, with rockets, the most power you'll put out is 1,500 watts.
So can you explain that again? Peak envelope power is the maximum?
Sure. Yeah, sure. So there's different ways to measure power, okay? The one way to measure power is peak envelope power. So what we're saying here is if we look at a wave, right, let's say on whatever, 40 meters, okay, and we're looking at the power output, the maximum power that we can put out, the maximum power of this envelope, okay, would be 1,500 watts. So the highest peak you can get, full crank, you know, pedal to the metal kind of thing, 1,500 watts. That's what peak envelope.
Out of your antenna.
Out of the antenna.
So
right.
Maximum wattage out of the antenna would be 1,500
Right.
watts, you're saying?
Correct.
Okay.
Right. Now, that's not my favorite way of measuring power, but that's what the FCC wants you to do, so that's what we go by, okay? The only exception to that, okay, is 200 watts on 30 meters. That's the band that we can't use phone on, right?
Right.
And for beacons, 100 watts max. Beacons are those those radio transmitters that hang out all over the place that are great devices for us to see how propagation is. All right, so these beacons are all over the place. They're basically just transmitters. They transmit a constant signal. I think the one in New York is in the UN, right? In the UN. Yeah. I think the most popular one is at the top of the UN here in New York. Okay. All right. Cool. RTTY. Okay. RTTY is a digital mode, as we know. Okay. And one of the questions might be, where is RTTY located? It's always on the lower sideband, and this is where RTTY is permitted on 80 meters, on 20 meters. Okay, so this is just straight memorization. So it doesn't matter if you take the general course or not, you still have to memorize these things. All right. And then one question would be the maximum symbol rate for packet, RTTY, or data, and it varies depending on the frequencies, and here are the values. And unfortunately, you need to know those. Okay? These are the possible ones that you need to know. All right. What's interesting, and something I forgot to put in these notes, once you get your general license, assuming you already had your call sign under technician, so as a technician, my call sign, Whiskey 2 Bravo, my papa. The moment I pass the test, and I explained this in the technician course, the moment you pass your test, as a general, you receive general privileges. So what you do is, if I'm a technician, W2BMP, and I pass the general, I would be W2BMP/AG. AG for general. And when you pass your extra, W2BMP/AE. Okay? The other thing that I forgot to mention and put in these notes is, they're going to talk about you becoming a volunteer examiner. You have the right to do that once you have your general license. One question on the test that I forgot to put in here is, as a general, the VE, who can you examine? You can only serve as an examiner for technician class, not technician in general, and not technician general and extra. You can only grade the exams for a technician. I forgot to put that in there, Wayne. So.
Okay, yeah, I remember I was seeing that. As a general, you can only grade the class below you, but you can administer.
Right. Okay. And that is one of the questions on, I think, test number 4. Anyway, minimum channel separation. These you need to know. CW, obviously the smallest one. This is in hertz, from 150 to 500 hertz. On single sideband, you want 3 kilohertz separation between signals. Otherwise, it becomes a mess. Okay. All right. Power multipliers, the ones that we learned, right? So we learned 3 dB, 6 dB. We had 10 dB, which is 10 times. And now we added 2 more. 20 dB is a 100-fold change. And 1 dB loss is minus 20.5, right? So these are the ones that you needed to know. Also make note, one question that's on every exam is, what does 1 S unit on your meter, on your radio equal? 1 S unit equals 6 dB. Okay. And I'll go over this again, so don't get too flustered if I'm feeding you too much information too quickly. Okay. PS31 uses a protocol called Barricode. Okay. And RTTY uses that 5-bit Bordeaux code. So that you should have remembered from your technician. So I say Bordeaux, you say RTTY. Say RTTY, you say Bordeaux. Okay. Okay. So I have Luz sitting next to me here, and he's not going to like what I'm about to say, but hey, what can I tell you? We agree to disagree, and that's the sideband operation, okay? This is what the ARRL wants you to know, okay? So if we are below 14 megahertz, then we take a frequency below 14 megahertz, okay, 20 meters. We go lower than that, okay? According to the ARRL, and they know everything. Oops, wrong one. Hold on. They want you to use lower sideband, right? So if I'm here, okay, my mode here in the upper left-hand corner should be lower sideband. All right? Can you see that, Wayne?
Yes, I see it.
Okay. So here is what we're interested in. We're supposed to be using lower sideband. Okay?
Yep, gotcha. I see it.
To their infinite wisdom, okay, if we go above 14 megahertz, okay, so anything above that, as we move forward, they want you to use upper sideband, right? So when we go into, let's say, 17 meters, we should be in upper sideband. Okay, that's their interpretation of it. Okay, it has been my experience. Well, first of all, that's just in a gentleman's agreement. Okay, so there is no hard, fast rule or regulation. It's just an agreement. Would you agree?
Yes.
Okay, so Lou's agreeing. That's pretty good. Okay.
There you go. Way to go, Lou.
Yeah. My experience has been that that's kind of a little bit of old school and optimistic thinking. The bands get so crowded that they're all over the place. Okay, so you could be on 40 meters, and it could be upper sideband, lower sideband. So from a practical experience, I don't really go by that personally. But what I think personally doesn't matter at this point.
It's a convention.
It's a convention.
And if it's followed, it's a little bit more civilized.
And I agree with that. However, not everybody on amateur radio is civilized. Okay, so they're all over the place. So the ones that I need you to know, so below the 20 meter band, lower sideband. Above the 20 meter band, use upper sideband. That's the general rule of thumb. So look for that 14. If the number is below 14, then you know it's lower sideband. If the number is higher than the 14, upper sideband. That's the easy way to remember the answer to the exam. Once you get your license and your radio and you're all over the place, you make your own decision, or the people actually follow that convention. Okay. All right. Propagation. So in the technician class, we just discussed propagation in a very broad sense, right? And now we define it a little bit more. And there are indexes or values that we can look at to determine what the propagation is really like. Where do you find that? There's a million sites on the internet that give you this information. Just Google ham radio propagation and 50 million sites. Is there a like propagation?
Not particularly.
Yeah. So refer to two different values here. What? So I lost. Oh, we got more people in. We got 9 people. All right. So hi everybody. If you have any questions, just hop right in. Okay. So propagation, the A index. Okay. The A index is the long-term magnetic stability. What's happening long-term? Normally the cycle is 11 years. Yeah, it's about 11 years.
The overall
yeah, so
sunspot cycle.
Yeah, the sunspot cycle, the geomagnetic, it varies depending on what's going on in the planets around us. So the long-term stability is on an A index. The K index is short term. What's happening today, what's happening tomorrow, happening this week. So A index, long-term stability. K index, what's happening right now. Okay? They measure solar flux. So solar flux is the amount of electromagnetic energy spinning around all over the place. We call that the solar flux, and it's measured at a radio frequency of 10.7 centimeters. Why you need to know that at this level, I'm not really sure. It's a question on the test. Don't say I didn't tell you. Okay? So, we go into the atmosphere a little bit more. D layer absorbs radio frequencies. E layer will give you a hop, okay, of about 1,200 miles. The F2 layer gives you a hop of about 2,500 miles. Right? Low frequencies are good at night. Okay? So the low frequencies are these guys here. So at 80 meters, 60 meters, 40 meters, they're usually better at night. Okay? And they're good at night, and the higher HFs work better during the day. So 10 meters, 12 meters, 17 meters. 17 meters a little iffy, but what do you think?
Well, the one thing I was going to say is the D layer. Thing to remember is it's the daytime layer.
Yeah, that's a good way to remember it. That's a good way to remember it. Okay, maximum range on a frequency is just below the maximum usable frequency. Okay, and the short range, we refer to these two terms, maximum usable frequency and lowest usable frequency. All right, and we'll discuss that a little bit more in detail. I'll tell you what that's all about. All right, the next sentence here, they love to ask you questions about. Okay, so here's the way it works. The sun is 8 minutes away from us. So if the sun blew up 8 minutes ago, we still wouldn't know it. Okay, or just about starting to realize it. If the sun blew up 5 minutes ago, we wouldn't know it. So it takes the X-rays and ultraviolet rays from the sun 8 minutes to reach it. All right? So if the sun went away, we wouldn't know it for 8 minutes. However, the sun is very, very violent, and we have these sunspots or coronal mass ejections. That energy does not travel at the speed of light. Okay? So X-rays do, ultraviolet does. They travel at 186,000 miles per second Energy from CMEs do not travel at the speed of light, and they take 20 to 40 hours to reach us, depending on what's in the way. Okay? They love to ask that question. So, if a sunspot occurs, we can be affected by it in about 20 to 40 hours after it occurs. This occurs much more frequently than the general public is led to believe. And we do have radio blackouts, aircraft is affected, radar is affected, cable television is affected much, much more frequently than Joe Sixpack, the average consumer, is led to believe. You agree, right?
They only tell you when the really big ones happen.
Yeah, they only tell you when the really big ones happen. The reason we want you to know this is if you're on 40 meters and we've had a CME, you're going to notice it right away. The band is dead. And why we want you to know that this is. Okay? All right. And again, I don't make up the exam questions, and I don't understand why they do a lot of this stuff. All right, so one question that comes up is, how do you test for linearity? Consistency. Think of linearity as consistency. in your machine, in your receiver, okay? And the answer is you use two non-harmonically related audio tones from a tone generator to test the linearity or the consistency of your receiver. It will be on every single exam, okay? So this question, that's why I put it in bold, is on every single exam. So what they do is you buy your radio and you drop it at least 3 times, or war gets into it, or your nephew comes over and decides to paint it with a Crayola crayon, or your wife says, oh, that's a great place to put my cup of coffee. It's on top of your radio. The whole house, but she's got to put it on top of your radio because it looks better there. Or waters a plant on top of your radio, or whatever. And all of a sudden, you notice that you're not receiving. The selectivity and the sensitivity isn't very good. So you have to take it to your local radio technician, and he will do a 2 non-harmonically related audio tone test to realign your receiver. Basically, that's what that means. Okay? So as generals, you know, when a technician comes up to you and says, my radio isn't working the way it was, you can pick up your head, shake your head knowingly, nod your head knowingly, and said, yes, you should really have a linearity test, which is done with a 2 non-harmonically related audio tone. And the technician will say, wow. And then he'll feel good, and you'll feel good, and it's all good. All right.
2 non-harmonically related
Yeah. So every signal
tones.
Yeah, every signal that you put out, you know, you and I talking, a note, any note, they have a specific pattern, okay? And it's not just that one signal. So if we use concert A as a tone, for example, that's 440 megahertz. I'm sorry, 440 hertz. Thank you, Lou. 440 hertz, okay? It's not just this signal all by itself. It produces harmonics, and there's a mathematical formula to compute that. There's a harmonic at half that wavelength. There's another harmonic above it at 1.58 times, all right? And it's these harmonics that make, we don't necessarily perceive them, but it makes the note sound great. What this 2 non-harmonically related audio tones does is, let's say he'll tune that A440 as one tone, and the radio will receive it, and then he'll take another tone at, whatever, 333 hertz. I'm making this stuff up, by the way, folks, okay? And using this 2-tone test, he's able to see how the receiver receives the signal. And he makes the necessary adjustments. Does that make sense? Yes? No?
Okay. Yeah. Okay.
Yeah, so it's just so that we get a good sampling of how the receiver is receiving. Okay? Because if we used harmonically related tones, then one thing would sound great, and as soon as you tune to a different frequency, it would sound crummy. So, for example, this is not the world's best antenna. I hope you can hear that. So, as we start tuning this, you'll see that the pitch changes. Let me see if I can find something. That's really the same signal, okay? But as I start tuning differently here, if you notice the tuning changes, okay, and I'm working here, right? So as I start to change the frequency, it sounds different. And in order to get the best consistent overall performance from your receiver, remember, if you can't hear them, you can't work them, right? So if you can't hear them, That's a problem. That's why we use this two-tone harmonic test. So we get the best possible performance over a wide range of frequencies. Does that make more sense?
Yeah.
All right, cool. QRP, if you don't know this one, I quit. Okay, that's me. All right. You never heard of me, and, you know, one of those, you're going to make me look really bad, you'll get me kicked out. Okay. QRS, okay, S, slowly.
My favorite CW signal.
Is that right? Send more slowly. Lou says it's his favorite CW signal. Send more slowly. QRQ, send faster. QSL, acknowledge receipt. Okay. QRV, ready to receive. And this stuff is really used a great deal in CW, continuous wave, Morse code. Okay. KN is we're listening for a specific station. So we would put, KN W2BMP. So we're listening for a specific station. CL, we're closing the station. And AR, end of message. And again, these are CWs. You will hopefully get into CW at least at some point, and you'll understand what a great advantage CW is. And you can literally talk to the world on less than 1 watt. Very efficient. And it's a lot of fun. Okay. All right. They talk about wire sizes in the electronics version and in the electronics section. And the only thing you need to know, okay, is that a 15 amp circuit requires 14 gauge wire, and a 20 amp circuit requires 12 gauge wire. Okay. Those are the only 2 questions on the test. The point of this is very few, if any, HF radios come with their own power supply. So you have to hook them up to an external power supply. And they don't want you using the wrong wire to connect your radio to the power supply. Remember that you're putting out more power. Undoubtedly, I have no doubt, your first HF will be at full power, 100 watts, smoking because you want to talk to somebody in whatever, in South Carolina or Europe. You got to talk to them. You're going to get through no matter what. So you crank up your radio to 100 watts. And if you have the wrong gauge wire going from your radio to your power supply, guess what's going to happen? Fire, smoke, your smoke alarm's going to go off. You're going to hit your significant other. The dog will start barking, all sorts of mayhem. So
voltage will drop and you'll lose power.
Your voltage will drop, you'll lose power, you'll probably damage your radio in some way. Not a good thing. So these are the two most popular amperage that we use. Okay. Normally, the power supplies that are most common are rated either 30 watt, 20 watt, 30 watt, or 35, 40 watt. Okay. And they want you to know that if you're going to draw this much amperage, okay, you should use this this gauge wire. So depending on how efficient the radio is, it will draw different amperage. Okay. So my ICOM IC7000 that we've been working with is not very efficient. So it draws about, I don't know, it'll draw about 8, 9, 10, 15 watts, 15 amps rather. I do have a radio in the other room made by Yaesu, more energy efficient. It draws a lot less amperage. But the point is, have the right size wire when you hook this up. Remember, part of this is we don't want you to get hurt. We don't want you to set fire to your dog. We don't want any of that bad stuff to happen, right? So a lot of it is about, being safe and making sure you don't hurt yourself. Because everybody gets excited, okay? When you finally get your general license, oh boy, I can go on 40 meters and talk to Japan. That's awesome. Just don't hurt yourself in the process. That's what it's all about. Okay. All right. So they give you all of these heavy-duty formulas to worry about, okay? So how do you want to do this? Do you want to hold on to this? Do you want to discuss it now, get the math out of the way, or do you want me to, you want to go over the easier stuff first? We'll take a vote. I can take it either by chat or by voice.
I'm good. Honestly, I'm good with the series parallel formulas. I've done that for many years, so whatever everybody else wants to do.
Okay.
An error in the first connector.
Huh?
There's a typo in the first connector. DB9 says DE9.
DB9, right. Okay. Let's hold on to the math for a little bit. And what I'd like you to do is I'll send out an email. I want to make sure everybody has their calculator handy, okay? Do not stress over this stuff, okay? How do I figure out 1 over? It is super duper duper easy with your calculator. Okay, that's why I had you select the calculator that I suggested. Super duper easy. I promise, I promise, I promise. So let's hold on to that for a little bit and we'll come back to it, okay? Reactance, okay? They want to know if you know what reactance is. Anybody know what reactance is? Anybody want to give me a definition for reactance? You guys are a bunch of chickens.
Is it
Yeah.
All right. Somebody tell me what reactance is. Peng, you want to give me can you type in a quick definition of reactance? Wayne? Anybody? Is this on?
Oh God, it's been a while.
It's very simple.
Reactance.
Okay. All right, so I'm going to define
Isn't that a measurement of inductance?
Excuse me?
Isn't that a measurement of your inductance? Not, I know it's measured in henries, but isn't it related, comparable to inductance or capacitance?
Yeah, pretty close. Very, very close. So I'm defining this not from an electrical engineering perspective, but I'm defining this as the ARRL and the FCC wants to define this, okay? So reactance is no-go. Think of it that way, right? So in a circuit, the flow of electrons, it flows through the circuit, everything is fine. But sometimes we need to resist that flow of electrons. And we use that using 2 major components. And that's a capacitor, which stores energy. The first one to type in the right answer wins a brand new Mercedes-Benz. Capacitor stores energy. I'm waiting. Type. Start typing. Go. Dun, dun, dun,
Capacitor stores electrical energy.
Okay. And inductors store energy.
Magnetic energy.
All right. Excellent. So we have these 2 major components. Okay. So we have inductors and we have capacitors. So the resistance to that flow of electrons via inductors or capacitors is known as reactance. Okay? As we apply the flow of electrons through capacitors or inductors, they tend to resist the change. Okay? They resist that flow of electrons. That resistance is known as reactance. Please do not go to an electrical engineer and define reactance that way, because after he stops laughing or she stops laughing, you'll have to buy him a drink, okay? So, but that, for our purposes here, that's what we're talking about, okay? So that's reactance. So inductors, capacitors, they resist the flow of electrons. That's reactance, all right? Okay, impedance matching. Impedance matching, very simple. We use inductors and capacitors to affect the highest power transfer efficiency possible. That was my tuner. Remember my tuner on my radio? I pressed the button and it did all of these strange things. And what happened was inside there's inductors and capacitors, and it matches the frequency, my radio, to the antenna. So it's transferring the power from my radio to the antenna most efficiently. These are called, so here's my radio, right? Here's my antenna, okay, or a skyhook as it's called. And then we have a tuner in here. These are sometimes called tank circuits, LC circuits. They call them all sorts of different stuff. But basically, it's just a tuner, okay? And I hook up my radio, the output of my radio, to this tuner, and from the tuner to the antenna. What this does is, using capacitors and inductors and a bunch of other stuff, it maximizes. So if I'm putting out 100 watts here, okay, at a specific frequency, let's say at 7.64, okay, which is the frequency I'm on, 100 watts, okay, what's coming out of my antenna is as much as possible. It's never 100 watts, all right, because we have that SWR to worry about too. So it's never 100 watts, but we get as much power as possible. Without this tuner, if this tuner wasn't here, only God knows what I would be putting out. Okay? Anybody would know. It could be 20 watts, it could be 90 watts, it could be whatever. And that's why you need an antenna tuner on HF. That's most obvious on HF, on high frequency. Okay? Please don't stress if you don't get all of this. We're going to go through it a couple of times. Connectors. Lou pointed out this is a typo. This should not be DE. It should be DB, as in boy, Bravo. Okay. That's the old-fashioned computer serial cable. DIN is that round plug that they use for car stereos. It looks like this. It's round, and it's got like these little doohickey things in there, these little leads. Okay, that's a DIN connector. RCA audio cable. RCA connectors are most frequently associated with audio. That's a question on the test. Okay. PL259, big clunky connector. I will show you one next time when I have the camera hooked up. Okay. And the N connector is the most popular because it's incredibly waterproof. Okay. If you buy a Baofeng radio, or basically any HT, okay, what's connecting the antenna to the radio is an SMA, normally an SMA connector. Okay. All right. And we're going to go through the manual quickly and cover some other items. So, again, this is the stuff I need you to really kind of know, memorize, actually. This one we know because we learned this, even though we're not required to learn it for the technician exam. I taught it to you, the field effect transistor. And somebody tell me, what does the field effect transistor have that no other transistor has?
A gate.
That's it, because you got to go through the gate to get to the field, right? This is our diode, Roach Motel, right? Electrons come in, but they don't come out that way anyway. And if you put a Z, this is actually after a couple of margaritas. If you turn it on its side, it looks like a Z. That's called a Zener diode. And it's used for power regulators and things like that. Okay. Then they're going to ask you about this specific transistor. Okay, there are various types. The main types are PNP and NPN transistors. Remember that transistors themselves have no charge. There's no such thing as a positive transistor and a negative transistor. That's not what they do. Transistors allow the flow of either electrons or not allow the flow of electrons through them. Okay, hence their name. And they're going to ask you about this NPN transistor. The NPN transistor, okay, I'm going to zoom in here. The NPN transistor's got the little arrow facing outward. This little guy right here, okay? It's trying to bust out of that little circle. That's how you know it's an NPN transistor. Okay? So you know what the gate is, you know what a Zener diode, and NPN, you know what that looks like. All right? All right. Cool. We're up to 10 people. Wow, I didn't think that many people were going to show up tonight. Well, thank you. Anyway, let me switch back here. This is a transformer, this bad boy right here, okay, that we're looking at. Hey, that looks like an inductor, doesn't it? It looks like two inductors. Because I told you that the thing that looks like a chicken fence is an inductor. That's two inductors, ain't it? Well, basically that's what a transformer is. Okay, hold on one second. Sorry about that, guys. So a transformer is really just two inductors, okay, together, and that's what a transformer is. And a transformer changes one circuit into a different type of circuit. AC to DC, you can change the voltage, you can do a whole bunch of different things. Okay, that's what a transformer does. And tapped inductor looks like this. I guarantee you that you will have one of these on the exam, but not too bad because you already know most of them. Okay? All right. This happens to be the dumbest set of two questions I have ever seen in my entire life. Why you would need to know this is totally beyond me. I hold an extra class license, and it's of very little value to me, okay, except if I'm building a kit. And then I just follow the instructions. All right. But you know what? That's our tax dollars at work here. Okay, think of it that way.
Actually, it's all done by volunteers.
That's right. We don't even get paid. That's true. That's true. So anyway, what you need to know for the exam, don't ask me why, because I don't know. Do you know why these are on the exam?
They are done by a team of volunteers who put together the question pool.
Okay, did everybody hear that answer? It's done by a group of volunteers who put the question pool together, and obviously there's an electrical engineer in the pool, okay, who just wants to make sure that you've read the manual, okay? You will have one of these two questions on your exam, okay? So you need to, the most popular one is the bottom one, okay? That appears in 4 out of the 5 exams. And then one of you are going to be lucky enough to get the top one. All right, so we have to learn both of them. So a germanium diode junction threshold voltage is 0.3 volts. A silicon diode junction threshold voltage is 0.7 volts. That's it. All right, don't ask me why you need to know them. Don't ask me to put them in a practical application. Don't ask me why. I just don't know. Okay? All right, cool. I told you we're going to leave the math for next class. So we're going to talk about this peak envelope power, how to compute it. Okay? All I want you to know that that's one measurement of power is peak envelope power. For me, a much more meaningful measure of power is RMS, root mean squared, okay? And they also talk about peak-to-peak voltage. Don't stress over this. There's only 8 possible questions that they can ask you. So if you memorize the questions, you'll know the answers. I will explain how to compute this, but don't stress over this, okay? Here are our 2 friends, EIR, PIE. We know how to do that, upside down and backwards. And here's a new one for us because we were getting bored. We had nothing else to talk about tonight. Okay, that's this guy here. And this is a way of computing power and resistance in the same circuit. Okay, so if you remember here in these 2 other charts that we have, we couldn't really evaluate a value for resistance using these formulas because one is here and the other one is here. So we couldn't we couldn't really equate power to resistance. We didn't know how to do that. Now we know how to do this. And again, I'll go over the math with you next class. I don't want to freak you out too much. Okay? All right. They talk about logic circuits. And the logic circuits can do various things. So they're integrated circuits, and they will either act on something or not act on something, depending on their nature. Okay? There are various types of gates, and they're exactly as the name implies. They either let something happen or don't let something happen. Two most popular are AND, A-N-D, or NOR gates. Okay? So what this means is there's a guy in there, okay, and his name is Ralph. Okay? There's Ralph right here. Some of you know these formulas, and it sounds like you're electrical engineering students. So if you're going to cringe, go ahead, but I'm going to explain it this way anyway. Okay? Just an easy way to understand what's going on. Here's Ralph. He's my buddy. Okay? All right. And he sits in front of a keyboard. All right? And the keyboard has only 4 buttons. Okay? 2 highs. Let me draw this bigger. Why am I drawing this so small? Okay. So here's Ralph's keyboard. Okay? And it's got 4 buttons. And 2 of them are high values, or 1s. Okay? Computers only know about 2 numbers, basically, 0 and 1. 0 being off and 1 being on. Right? A little computer theory in here. Okay? So a computer works on this principle. So let's say high, on, or high. Okay? So 1 is high. Right? So we have 2 high buttons and we have 2 low buttons. Lows being 0s, highs being 1. And he has 2 options. Okay? Pass, let it go through, or no way, Jose. Okay? Or not pass. So when a signal comes in to one of these gates, the first thing Ralph does, and he says, okay, what do I have? Do I have a high, do I have a 1, or do I have a 0? In an AND gate, and there are many of these guys attached, so there could be an AND gate, an OR gate, there can be many other gates. If it says, okay, I have a high and I have another high, I'll let it pass. Okay? On a NOR gate, okay, it says if I have a high and a high, this is an AND gate. An OR gate, the problem is I can't erase just one little bit, unfortunately. So let's see if I can do it. So this is what an AND is. AND says high, high, okay. A NOR gate says if I see high, high, no pass. I'm not going to let you through. Okay? Or I'll make the signal low. So basically what I'm trying to tell you is that these gates are logic circuits. Okay? And they evaluate the output. Is the output high or is the output low? Is it a 1 or is it a 0? What's happening? And based on that information, it makes a decision. Okay? That's what gates do. That's a very, very rough, and I'm sorry if I offended the electrical engineers in the audience. Okay? But for our purposes, that's what they do. Okay? We're almost done here with this, and then we'll get into it in a little bit more detail. Okay. They came up with this fantastic formula, dipole length. Okay? And they talk about, remember that this is dBi, I being isotropic. That's this guy here. The ideal antenna, isotropic, always has the I. That's isotropic. So the length of a dipole antenna the length in feet, is equal to 468 over the frequency in megahertz. That gives you the absolute perfect isotropic dipole. Okay? And if you want to compute half of that, a quarter, et cetera, et cetera, don't get too tied up in this. Okay? This question only appears once in all 5 exams. But the general formula is 468 feet over the frequency in megahertz, and it will give you the length of the dipole in feet. Okay. All right. Then if you look at the different types of antennas, you'll see they have quad antennas and delta antennas. All right. And we'll talk about how to compute that a little bit later. Okay. But I want you to know that quad antennas exist. They're basically boxes. Deltas, they look like triangles. Okay. And on every single exam, that's why I underlined it. Okay. They ask you, what is the maximum theoretical gain of a 3-element Yagi? The answer is 9.7 dB I. I being isotropic. In the perfect, absolute perfect world, which doesn't exist, a 3-element Yagi, no matter what you do to it, no matter how big it is, no matter what you do, the maximum theoretical gain you could have would be 9.7 dB. Okay. Again, these are questions, these are the things you should study to hopefully have a chance to go through and pass the exam. A lot of it's memorization, and I understand that. Okay? So, but this will give you at least a fighting chance to pass the general exam at the same time that you take your technician's exam. Okay, did I confuse everybody beyond total recognition, or where are we?
No, that was pretty harmless.
All right, cool. All right, so we're going to go through this very, very quickly, and I'm just going to highlight the points I think you should know. Okay, so the general manual is much shorter than the technician. All right. Okay, so chapter 1 is hams, you know what we do and where we go and what we're doing, blah, 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 how much to read, all about the ARRL, okay, what a great organization it is. Actually, it's pretty good. They do a pretty good job, okay. Introduction, basically what it's saying is, okay, you want to be a general, be careful. You can have more communication frequencies. So you have more frequencies to play with, basically all on HF, okay? You have more options. You can get into that RIDI and Pactor and Winmore and all sorts of junk, okay? And that'll keep you busy for the rest of your life, okay? This is the band plan, which you saw. Google band plan general, or I'll even send it to you. I'll email it to you tonight. You'll see that your privileges as a general are pretty extensive. There's only a couple of places that you cannot go, that I can go, and if you want to go there, take your extra, okay? All right, cool. Your exam will be exactly the same as your technician exam. You need to get 26 questions correct, okay? And let's see, a bunch of people hanging out. No Morse code requirement. And that's fine with me, no problem. How to use this book, read it. All right, cool. Advanced students, self-study, blah, blah, blah. And we're just whipping through chapter 1. No problem. We finished chapter 1. There we go. Okay. So what they want you to know here is, as a general, you're going to look at different types of antennas. You're going to see how to operate more efficiently on single sideband, how to get into things like PSK31, the effects of the universe that we live in, how does that affect radio transmission. The reason is we don't want you to get frustrated. You spend $2,000 or whatever on your radio, you almost kill yourself putting up your antenna, you go and you measure the SWR, everything is perfect, you go out and you buy a antenna analyzer. You do everything I told you to do. You turn on 40 meters, and nobody's there, and all you hear is static. We want you to understand why that happens, okay? And that happens sometimes, okay? So we don't want you to get frustrated. Patience and a little knowledge here. You'll take the same exact type of test. You'll fill out this form, the 605 form, and off you go. And as soon as you pass the technician exam, you'll tell them, I'd like to take the general, and you go through it. Normally, if you do not study for the general exam at all, the average result is you get 14 or 15 questions correctly. So with a little push, I think you can do it. Okay. All right. There's junk here, a bunch of stuff that's not on the exam. Okay. And they want you to go in and build kits and do all sorts of cool stuff. Yeah, go ahead and do that. It's a lot of fun. It really is a lot of fun. Okay. All right, cool. All the stuff that's going to be covered in the exam. Forget that stuff. Blah, 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 blah. All right, cool. All right, procedures and practices. Okay. Basically, they are exactly what I told you that they are. All right. And you know how you break in. Again, there are very few, if any, repeaters on HF. Okay, so there'll be no tone. You just pick a frequency, or you'll scan a frequency. You'll wait for somebody to come on, and when the conversation breaks for a second, you hit transmit and your call sign. That usually will get you in. Okay. On HF, there is a net for everything you can possibly imagine. So it's a bunch of people who talk about anything. Saturday mornings, there are nets all over HF worldwide. Okay, so you can. I think there's a really cool net on 17 meters worldwide, and it originates from England, and it's very cool. And you can talk about a whole bunch of various different things. And we know that when we want to make a call on HF, we go CQ, CQ, CQ. So there's nobody talking. It's an empty frequency. We are calling anybody. Okay? CQ, CQ, CQ. This is for Morse code. When we want to say from, it's DE. We learned all this stuff, right? CQDX means distant station. So if you don't want to talk to somebody from Brooklyn, that's okay, although Brooklyn is considered by many to be a foreign country, and you want to talk to, let's say, Europe, you would do CQDX. CQ, 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 CQDX, CQDX, and you may get a response. The most common frequencies, the most common bands, they're all pretty busy. Would you agree, Lou? 20 meters, 17 meters, 40 meters?
Yeah, depending on the propagation and the time of the day and the week.
Yeah, so depending on the propagation, and you can find that on Google, and whether you're going to use the morning or the afternoon or evening, it gets busy. It gets really busy. 80 meters gets really busy. 40 meters gets swamped. Okay, and you never know who you're going to talk to. Okay. All right, cool. Selecting a frequency. You select basically whatever pleases you. Just remember, please don't go on 30 meters and use phone. Don't use your voice. Okay, you'll piss off everybody. Okay, and make sure you stay within your allotted frequency. Okay, please don't go into an extras area. Again, the rule is because if I make a contact with you and I'm doing it on 1 watt and you're in California, I'm going to write it down in my logbook, and then I find out that you don't have privileges there. I just wasted my time. Okay? And you shouldn't be there anyway. Okay? All right, cool. Nets and schedules. Just do ham radio nets on Google. There's a gazillion of them. Okay? I didn't get into it too much because I don't do it much. Okay? As a matter of fact, I very rarely do it. there's contesting, okay, and there's an award for worked all states, worked all countries, worked all planets, whatever, you know. And I'm not into contesting. The way it works is, and I think it's kind of silly to be honest with you, but that's just me. You get on the radio, and some guy's going, CQ, 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 W2BMP. And you get on and you go, hi, I'm W2CTG. You don't even say hi. You say, W2CTG with you. They'll say, okay, thank you. I read you 5 by 9. Remember that 5 by 9? Your signal is strong and I can hear you well. Even if I'm not 5 by 9, he'll say I'm 5 by 9. You're number 147. So I'm the 147th contact that they made. To me, that has limited appeal. Okay. What I do like is I do like the special events. Okay. And as I said, we can talk to the space station. We can celebrate the Lusitania, the Titanic, Lindbergh. And that's just our club. Okay. There's a million special events. Some of them are worldwide. I think there was one over the summer, Lusitania, right? And we talked to Ireland and England. And,
yeah.
Yeah. It was actually pretty cool.
I like the Lighthouse and Light Shift weekend.
Yeah, that's true. I didn't think of that. So we have lighthouses. All the lighthouses on the planet Earth get together. That's very cool. And basically you take your radio. We have a couple here on Long Island. You take your radio and your gear out to a lighthouse on Long Island, and you try to talk to the other lighthouses. It's very cool. Okay. All right. They talk about the frequencies, how they work. This happens to be on 20 meters, but the principle is the same. The beginning of the band, and I'm going to try to put both of these up here at the same time. Let's see how that works. Okay. I'm going to shrink it down here a little bit. So on 40 meters on hold on 20 meters over here. Okay. So at the beginning of the band here, we reserve that for RTTY. Okay. In this area, actually this goes this thing about here, and then as we move up the frequencies, they're used for different things. Okay. This happens to be PSK31, which is another digital mode. It's the general calling frequencies. So you meet somebody here at this frequency, and then you move to a different frequency. Okay? So it's cool. So everything has a plan, is what we're saying. Somebody came up with a pretty good idea. All right. Housekeeping and operation support. Keep a log. This is what a log looks like. Okay? Most of it is computerized now. That's the easiest way. If you use a program like Ham Radio Deluxe, it'll automatically enter the call in, and enter the log in when you make a contact. And it's cool to know all the people you spoke to. Okay. Managing interference. Remember, there's two types: QRM, man-made interference. That's the wackadoodles that live on the planet Earth with us, and jammers and accidental interference, generators, things like that, and QRN, which is natural atmospheric noise. Did you have a comment? No? Okay. All right. All right, cool. Avoiding interference. Just be careful of what you're doing. Make sure that you're not a source of interference, especially when you, of course, you will always adhere to the legal limit of 1,500 watts, except for those guys who live in Texas. They're not required to, no, they are required to do that, but they have more money than they know what to do with, and they end up, these are the guys who have family on Jupiter, okay? So stay away from them, okay? Reacting to interference. Sooner or later, you're going to run into a jammer. That's a person who is unlicensed and decides he just wants to have some fun. The general policy is never engage a jammer, okay? Never report back to him. It's actually illegal for you to do so. So if a person hasn't identified themselves, hasn't given you their call sign, then and is causing a ruckus, do not respond to them. That's what they want. Move to a different frequency. Modes, everybody knows about the modes. If you're taking your general and you don't know what CW stands for, you have a problem, okay? Amplitude modulation, single sideband phone is what we work with. That's that upper band, lower sideband, upper sideband thing, okay? Digital modes, there is a digital mode for everything, Pactor and Winmore they talk about here. And PSK31, Contesta, there's a gazillion different digital modes, all fine-tuned for whatever you're doing, okay? One of the cool things you can do is image modes. You can actually send television images and pictures. You can send it by slow scan TV. As a matter of fact, ICOM, one of the radio manufacturers, sells a handheld transceiver with a camera built into it. You can take a picture and transmit it on a frequency. And if somebody on the other end has a similar handheld receiver, an HT, they can see the picture, and you can send it over the air.
Historical note?
Yeah.
This method of slow scan TV is how we got the first pictures back from the moon.
That's right. That's right. Everybody hear that? So the slow scan TV is how we got the first pictures from the moon. Actually, we still get them in a similar method. However, they're now done digitally for more efficiency. Remember that the Voyager, which is 28 billion, that's billion with a B, miles away from Earth, is still transmitting on a 5-watt transmitter. You know that? 5 watts. And it gets to Earth. Okay? All right. This is a mode comparison. Basically, the ones that I want you to know, upside down and backwards. CW, tiny, 150 hertz. Single hertz, single sideband, 3 kilohertz. That's the 2 questions on the exam. CW, tiny, single sideband, kilohertz. If I sound repetitious, it's because I want you to know this so you snap to the answers there. Okay? Receiving, we talked about this at the last class, selectivity and sensitivity. Okay? Selectivity is once we get a signal that we can latch onto that person, and they will drift from us because of atmospheric and other conditions. So being able to selectively attach to somebody, big trick. That comes with a little finesse. Remember, it's called the art of radio, not the science of radio. Although there's science in it, you got to kind of know how to play it a little bit. That's really cool for me as a QRP guy. I'll talk to somebody in Europe, for example, because of the nature of my signal and their signal. They're anxious to talk to me because I'm QRP, right? They can talk to anybody on 1,500 watts. A QRP guy, especially if I'm pedestrian mobile, I'm walking around with my radio, that's something, okay? Now, they're going to have to adjust as I move around and the atmospheric conditions change, and that's called selectivity. Generally, the more expensive the radio is, the better selectivity it has, generally, okay? Sensitivity is the next term. If you can't hear it, can't hear the station, you can't work the station, to how sensitive my radio is. And of course, every manufacturer says that they have the best sensitivity and selectivity of anybody else on the planet. Don't believe everything you read. Okay. Any questions so far? We're good? All right, so as you get into HF, they have all of these doodad things on your radio. And they have notch filters and clarifiers and band filters and all sorts of stuff. And that's all so that we have better selectivity. We can latch on to a station that we want to talk to. That's all that means. Okay? So it's just stuff so we can receive clearer. Okay? Everybody knows what a RIT is, right? So receiver incremental tuner. Okay? We now have a thing called XIT, transmitter incremental tuning. So we can find, here's mine. Let me show you mine. Okay, so here's mine. So if I'm on this particular frequency, I don't know, let's pick one. Let's pick 14150. Here's my XIT, my fine tuner, and you can see that the frequencies move very, very little up here. This guy here. So it's fine tuning for transmitting. Okay. So if I'm not quite getting through, I can tune a little bit off frequency. The reason is, as the radio gets older, no machine made by man serves us forever. It fails. Components start to wear out. My antenna could be off a little bit, whatever the issue is. So if you're not hearing me clearly, I can move up little tiny increments at a time. Okay, a thousandth of a hertz if I have to. I can tune that fine, and they can usually get me better. Okay, called XIT. So just like receiver incremental tuner, there is an XIT for transmit. Okay, phone, everybody knows what that is. Push to talk button, right? And then they have this other thing called VOX, V-O-X, okay? Voice operated transmit. That's perfect if you're on a motorcycle. And that's the only place I think you should use it, okay? Every radio has a VOX function, even the little Baofungs. I accidentally left mine on and had a heated discussion with the dog, which I lost, by the way. And everybody at Linearity 146850 heard that conversation. That happened about 5 years ago. I have since permanently disabled all VOX operations on all of my radios. Okay. Very embarrassing. Okay. Very, very, very embarrassing. And that's why they elected me president. Anyway, so yeah, so VOX, hands-free operation. I suggest you use that with great prudence. Okay? Anti-VOX, that's me. Okay. So yeah, you make sure you have to turn it on by default. So by default, it's off. Thank God. You have to turn it on, and anyway, be careful with that. All right, signal reporting. We discussed this in the technician class. A 1 to 5 signal strength. Clarity, 1 to 9, okay. You say, I'm sorry, 1 to 5 being readability. So how good do you receive my voice or my signal, my CW signal, and 1 to 9 being my signal strength. And of course, when you go on a contest, everybody's 5 by 9, because you don't want to make them feel bad.
Even when you can't hear them.
Even when you can't hear them. Thank you. Even when you can't hear them, you're 5 by 9. Morse code, see what that looks like. I cheat, okay. My CW is not what it used to be at one point, so they have these automatic electronic keyers with built-in programmers, or even better, go out and buy Ham Radio Deluxe. Actually, there's a free version. Hit the CW key, you type, hit enter, out it goes. You're transmitting at 100 words a minute. Everybody thinks you're the best, but of course you're cheating. You should really, in all seriousness, you should really learn some basic CW. Learn how to send SOS, okay? You never know. You never know, okay? And remember that on CW, you can reach the world on less than a watt, okay? So, CW, you need to know these examples. So, CW, that's a perfect example of a transmission. CQ, 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 DE from W1AW, W1AW, W1AW. The K at the end means I'm done with this. I'm ready. Talk to me. Okay? And their response would be, hey, W1AW, this is from WB8IMY. 3 times, okay. K meaning, okay, I'm done. Then more stuff, okay? And then we talked about these Q signals, QRS, or slower, QRQ. You don't see that too often. Then faster, okay? All right, 0 beat, what do they mean for that? What that means is try to send it back the way you received it, or vice versa, okay? make sure you're on the same signal, you're on the same frequency, and it also implies send it at the same speed. Yeah.
There's a historical piece to this. Today we use transceivers that by default they're transmitting and receiving on the same frequency unless you do some other adjustment. In the old days, when we had separate transmitter and receiver, you had to adjust to get them together.
Right. So in the old way of doing things, we had a separate transmitter and receiver. Thank you, Lou. And to be on exactly the same frequency was called 0B. That's right. Okay. Digital modes. We talked about that. Okay. And this is where all the digital guys hang out. This is their frequencies, more or less. Okay. And you can play with it here, not on the exam. Okay. And they talk about RTTY. RTTY is actually radio teletype. It's the old-fashioned, if you look in the 50s and the 60s, this gigantic printer, and it would make the devil's own noise, typing and doing all sorts of things. That was the original radio teletype. Okay. Pactor and Winmore, other digital frequencies. Winmore uses, you can send sound card. Yeah, they both use sound cards. And
Pactor doesn't use.
Pactor doesn't use them. Sorry, but Winmore uses. You can use it for mail as well. Okay. PSK31 uses a sound card, and it's cool because it has great error correction and very little space, and it uses any sound card on basically any computer. Okay. Then these are other digital modes that we use. These guys here. Okay. And they're designed to do different things. They're all referred to as multi-frequency key shifting, MSK, and you can use 16, 63, multi-tone. There's a whole bunch of them. I just need you to know that they exist, okay? The ones I really need you to know are the ones on the sheet, okay? So if I say Bordeaux code, Linda, if I say Bordeaux code, you're going to say, you remember, Linda?
I'm sorry, I was distracted by another question I have. If you say what?
If I say Bordeaux code, you're going to say what?
I wrote it down.
Right here. I highlighted it for you on the screen.
Okay, now that's what I was going to ask you, because I still see frequency. I don't see anything that you're writing. I only see 14.15.
Oh, I'm sorry. Okay. Okay, so what I want you to know is that RTTY uses the 5-bit Bordeaux code, BAUDOT. Okay. What was your question, Linda?
I was wondering why I'm seeing just your radio. I don't see anything you've been talking about. So I don't know if it's just my screen, but I only see...
It's your screen.
Linda, I had that problem last night. Try and refreshing your page.
Okay, thank you.
I'm sorry, Linda. You should have spoken up. You should have sent me a text. I'm sorry. What I'm doing is I'm going through the manual, page by page, to point out, just give you a general feel for everything, and to point out the ones I really need you to know. Linda, let me know if you still have a problem. Okay? Emergency operation, we know how to handle that. We discussed it in the technician class, right? Emergency communications takes absolute priority over everything else, period, end of sentence. And we have to be ready for that. I sent you a radiogram. You know how to handle that. And here's what the FCC wants you to know about emergency communications, how to handle it during a disaster, what you can and can't do, the safety of life and property, protection of property, station in distress, the Radio Amateur Civil Emergency Service, RACES, R-A-C-E-S, okay, ARES, which is Lou and I are both a member of, okay. Certainly know where they are. Look them up in your area. Say hello when you get your license, okay? I'm not saying that you need to volunteer for anything. Just know where they are, where they work, and our areas, for example, we have a core membership of about 35, I believe, members, and then we have an auxiliary, standby, right?
Reserve.
A reserve. And I recommend, this is a new skill set that you have, okay? Very important skill set. Again, Lou and I are both New Yorkers. We're old-time New Yorkers here. Nothing ever bad could possibly happen in New York. It's just not going to happen. It's just not going to happen. We're in New York. That happens out in Kansas someplace. It doesn't happen here. Wyoming, Louisiana. Guess what? We were wrong. It happens every place. So part of that is, all right, enough of that speech. Okay. You get the point. Okay. The stress calls, SOS, Mayday, Mayday. Lou disagrees with me here a little bit, and I'm okay with that. You say break, break. I've had that happen a couple of times, actually. Somebody said break, break. The world does stop to listen to break, break. But SOS, Mayday, Mayday, way to do it.
Yeah, what it is with break is that they vary in different parts of the country. In some places they use it casually, in other places they don't accept it casually. Here, if you use break in New York area, they're going to treat it like it's an emergency call.
Right. He's absolutely right. Okay, the rules and regulations, they haven't really changed, and there's a couple of questions. There'll be 2 questions on them. On your general exam, you'll ace them because you'll already know that. You know that we're in ITU Region 2. Okay, we know that our license is good for 10 years. We know that as generals, we can only administer examinations to technicians alone, period. End of sentence. So if a guy walks in looking for a general exam and you are a general VE, you may not give him an examination. Okay? That's it. That's all we really need to know. Bunch of forms, blah, 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 blah. We know about control privileges. We know about control operators. We know about remote. We know about all this stuff. So we don't need to go over it again. There's another example of the band plan for you. Okay? Blah, 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 blah. HF bands, 10, 12, 15, 17, 20, 30, et cetera, et cetera. Beacons, we talked about beacons, right? And beacons are just transmitters, so we know if we could reach them. They operate in, there are normally 18 beacons. The only
Joe, where'd you go? Joe, come in.
You going to teach the class, Wayne?
Yeah, where'd he go?
I don't know. He's gone, though.
Your audio dropped off.
Can somebody type to him?
I am doing that right now.
Okay.
Is anybody else on?
This is Dana. I'm on.
Dana,
I cannot hear him either.
Okay.
I do not. I am not hearing Joe.
Yeah, everybody text bomb him.
Yeah, I can't hear him either.
On a phone. Maybe he'll pick up his telephone. No, that's not his number. He's just rattling on. Hello, yep. Oh, this is just grand.
Excellent.
I'm going to shoot him an email.
Does anybody know, have his wife's cell phone number?
Yeah, I'm gonna shoot him an email, Linda. I don't know.
Yeah, I just checked his last couple of emails, and he doesn't have a cell phone or home phone. Only the connect to.
Oh look, now my whole page dropped off here. Let me see here. Let me try and log on.
Sorry about that. Can you guys hear me now?
There's
Where'd you
Joe.
go?
Sorry, we were taking a break.
Yeah, you taking a
I
break.
accidentally lost you. Sorry.
Going on
sorry.
hiatus, man.
Sorry. Where did you lose me? What part did you lose me on?
About 5 minutes ago.
Oh, I'm sorry. Okay. Basically, you didn't miss anything too much. Okay.
Okay.
We're just discussing the rules. They haven't changed. Okay. And then down here, this table 3.4. It's on your study sheet. How fast you can transmit.
Okay.
All right. There was nothing really to talk about. The rules are the rules. You know the rules.
What are these third-party traffic agreements here? These are just international agreements?
Yeah, so as generals, remember we have HF frequencies, right?
Yeah, yeah.
So you can actually talk to all of these countries on HF. And what this is somebody could knock on your door and say, I want to send a radiogram to Guatemala. Well, you're allowed to do that, okay? So you'll ask them what town they're near or whatever, and try to pick up a station in Guatemala and send a radiogram to that ham radio operator.
How would you initiate contact? CIV's
question. Good question. So you'd have to look to see kind of where they hang out. Guatemala does have areas. All the countries do. They have areas and races and that kind of stuff. You would have to look them up and try to get a traffic net near them. You could also get a standard traffic net, and they would probably know.
So you wouldn't be like your W2BMP to TG, blah, 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 right?
Right. So you can look up traffic nets for specific countries on the net, depending on where you need to go. Okay?
Yep.
All right, cool. So prohibited communications, don't transmit music except to the space station, usual stuff, okay? All right, cool. And then what do you put in the log? I forgot to cover that for you. And you put the date and the time of the contact, the frequency that you were on, the call sign of the station you contacted, and of course that they were 5 by 9. Okay. Lou's laughing in the background, and you know, what can I tell you? All right, cool.
A 5.7 and a 5.5.
Yeah. Have you? Have you done 5
today?
Did you? All right. Well, yeah. I guess if you want to be accurate, you can say 5.9 or 5.7 or whatever. Okay. Chapter 4. We're going to just look at real quick, and then we're going to call it a night. So we all know what current, voltage, and power is, right? How we play with that stuff. All right. Anybody have any question on that? All right. Resistance in the Ohm law. So resistance is defined as any opposition to current flow is known as resistance. It's measured in ohms, and we measure it with a device called an ohm meter. Okay. Remember that reactance? Somebody tell me what reactance is. I'm tired of talking. What's reactance?
It's the resistance of a capacitive and inductive circuit.
Yeah, okay, exactly correct. The opposition caused by a capacitor or an inductor. And they have different values. They're known as capacitive resistance and inductive resistance, or reactance. So, yeah. All right, anyway. So I hope everybody can see my screen. These are our 2 old friends, okay? And then we added one other formula here, which is here, and I'll try to make this bigger, okay? So we've added this formula here, and that's a way to compute power using resistance, or resistance with power. So now we found a way of being able to do that, and the formula is P is equal to I squared times R. There are no questions on the exams about this, okay? Even though they list them, there is no question on it. But again, if you want to learn how to do it, it's on page 4.2 of the manual, okay? And basically, it's the same as these guys. You just add this formula. All right? All right. We talk about AC and waveforms. We know that there's 2 types, right? There's direct current voltage and alternating current. No biggie there. Wavelength. Okay. So there is a formula to compute wavelength, and it's very popular. So this guy here, lambda, is the symbol for wavelength, is equal to 300, okay, over the frequency in megahertz. And that's how we compute what band goes where. Remember that is frequency in megahertz, right? If you don't use megahertz, then you have to add a whole bunch of zeros to this top line, okay? So just this is how we compute bands, right? And they make it sound very complicated, just a formula. It's not necessarily on the exam, but just so you know. Does everybody understand the difference between series and parallel circuits?
Yes.
Yes. Series, Christmas tree lights, right? And,
Parallel house wiring.
Excuse me?
Parallel is house wiring.
Yeah, you can do that. Yes, exactly. That's a great analogy. Okay. dB, we know about dB because I taught it to you. Okay. And this is the formula that they use for power. Okay. So dB is 10 times the log 10. Everybody knows how to do this. If you don't, let me know. It's the measured power over the reference power. Okay. Now they want you to also know how to compute dB for voltage. It's almost the same, but instead of using 10, it's 20 times. Okay? There is no question on voltage dB. There's only questions on this dB. And what I want you to know, okay, is the ones we just considered in our, here. This is what I want you to know. You know this, you'll get every question right on that. Okay? So 3 dB, 6 dB, 10 dB from the technician, 20 dB for the extra, and dB loss minus 20%. The question will be, you hook up your radio, right, 100-watt radio, and you only get 80 watts coming out of your antenna. How many dB is that? And you'll get 3 different answers. The right answer is 1 dB loss. We also call that 1 dB down. Okay? That's another way that we state that. Okay. And they spent a whole bunch of time on this, how to do this, but you guys know how to do this, no problem. Okay? All right. Calculating a power or voltage regulator ratio state. There's 2 things that you can do here. There are only 8 possible questions that they can ask you on the exam. Okay? You can either go to hamstudy.org and memorize the question and the answer, or you can actually try to compute this. There are no questions on the exam on this, calculating a power or voltage ratio from dB. There are none on the exam. So I refer you, I just don't have the time since we only have 2 classes. And I know some of you are taking your exams next week, a week from today. So I don't want to spend a lot of time on this. If you need to know how it works, then certainly look in the manual. Okay? I'm only going to go over the stuff that's actually on the exam. Okay? One thing I will go over with you, and because it is on the exam, is another way of defining power. And power can also be defined in RMS. Root mean squared. And it's possibly the most meaningful way to measure power. Okay? And it's an average, specifically an average. Taking the entire envelope, power envelope, into consideration. To me, it's the most valuable. So RMS, okay, would be as you take the average of this entire envelope. Okay? As opposed to peak to peak or peak envelope power. I mean, that's important, I guess, for the FCC when they don't want you to exceed a certain value. You know, they refer to peak envelope power here. Okay? But for overall performance, RMS is a little bit more informative. Not more valuable, but more informative. All right? And then they come up with a bunch of formulas for it. We'll go over one next Tuesday when we meet again. Okay? Peak envelope power, we just talked about that. Make sure peak envelope power, you don't exceed 1,500 watts. We would never do that as law-abiding citizens. There's no way we would do that. And Lou is smiling because he knows that that's not necessarily the case. I'll discuss these formulas with you. Do not stress over them. They're incredibly easy. Okay? I promise. All right? And one of the questions maybe that's not on the sheet is basic components. They talk about the temperature coefficient. Okay? So what does that mean? That means any component will vary in its performance because of temperature. Okay, as a general rule in electronics, performance is the inverse of temperature in electronics. So as temperature decreases, generally, the performance of most solid-state electronics will increase. That is not true of tubes, of vacuum tubes. Only for solid-state electronics. As temperature decreases, performance increases until you hit like absolute zero. Then nothing works.
All right.
All right. So they talk about these values, nominal value, what we can expect from it, okay, how much tolerance there is, plus or minus a percent, okay. Normally it's about 5%. Temperature coefficient efficiency is how the component will react under temperature, okay, and the power rating for that. The one that's on the exam, temperature coefficient. Okay. And resistors and resistance. We talked about that a little bit. We have the schematic, but you guys are pros at this. Look at the schematic if you can. I'll try to send you one for the general exam. I'll try to send you this page. Nothing really unusual. The ones you need to know are on your study sheet. Okay? Different types of resistors, and they have these stripes on them, and that gives you the value of that resistor. There's a little chart, and you can figure it out. Okay? Parasitic inductance. What does that mean? That means that every device will give you inductance just by being there. Just by being there. Okay? The device itself will give you some inductance. It'll cause the voltage to drop just by being there, even if the system is off. A good analogy to that is your car. Okay? Modern cars, even if you turn off the ignition, it's drawing amperage from the battery. And given enough time, if you leave your car and don't turn it on all winter, you go to turn it on in the summer, and it doesn't crank over. A perfect example of parasitic inductance. Okay. All right. Any questions? I know we covered a lot here today. We're going to stop here. This is exactly half of the manual. Okay. We're going to, on Tuesday, please have your calculators. We will go over computing some basic stuff. That stuff about capacitors in series and capacitors in a parallel circuit. Super simple. Those are the ones I want you to worry about, and you don't really have to worry about them. They're super simple. And we'll finish up next Tuesday. Any questions? No? I'm that good of a teacher? Holy cow. Wow. I'm impressed. All right, guys. Have a great weekend. You're doing great. Any questions, email me.
All right, Joe. Thank you. You have a
All right, good night, guys.
Thank you, Joe.
you have a good weekend yourself.
All right, bye.
Good night.